the proof is indirect somehow. It involves quite a bit of structure theory, and I'm convinced that there should be an easy proof based on the local compactness of the field, and the fact that over characteristic zero we have more than just here's something that you don't have over characteristic P, that orbits are open in their closure for transitive actions. Over the characteristic P, we've seen that orbits are closed, but not open. Right? Remember, we have this difference because we sort of had to extend scalars for some reason. So I think that whenever you have a G mod H, you can compactify it. You can find a projective representation of G such that H stabilizes the line, a point in the projective space, and there is a natural equivariant compactification. And if we can compactify G mod H in a way that respects the analytic structure, then and we know that orbits are open, by compactness we can deduce that they are finitely many. I think this is very reasonable to expect an easy proof along these lines. But again, I don't know. But if someone will pick it up here and prove it, I will be. But now we will follow the Borel-Serre techniques. And actually, I said that there should be a similar proof, but they actually prove a bit more. Because they use the following property of fellow there exist finitely many, only finitely many field extensions. Well, up to isomorphism, or I'm working in some fixed algebraic closure. Finitely many field extensions of every degree. This is not true for an arbitrary field, but it is true for a local field. I owe you the proof, I will postpone it. And the Borel-Serre actually show that F with that property and the characteristic is zero, or actually not immediately even that property will be perfect field, then H1 so we will not actually use the local compactness. In any case, only this lemma which I postponed the proof. So this is what I want to prove, and maybe let's just say something about gamma. Gamma is the Galois, the absolute Galois of F. So this implies as I mean we have correspondence between open subgroups of gamma and finite extensions, finite field extensions of F, right? So, sorry?
Gamma is the law of...
Oh, it's the absolute. It's F bar, comma F, yeah. As finitely many open subgroups of each index. Of course, this is a finite group, it's a compact group. Open subgroup is always a finite index by compactness, and this and that are exactly synonyms. So now I'll explain actually the most important case, which is the case of a finite group, and this will come about very naturally. mean, this must be the case if I hope to have this one. And the following case 1, which is case of the final group. Soon be. So by the way, even if we are interested, just with even if we are interested only with connected algebraic group, I will do a series of reductions, and eventually the case of a finite group will be very important. So yes,
H1FG is H1 Galois.
oh, it's H1 of the Galois. So gamma, the Galois group, act on GF bar, right? And but this is a finite group. So this is a map from this group into symmetric group subset. It has a finite image, and in particular a cofinite camera. It's the kernel of the action. I call it gamma 0. It's an open group of finite integers. And further, I will take even smaller group. N will be the intersection of all subgroups of gamma of index n times so this is some maybe huge index, and there are finely many open groups of this sort. This collection is closed under conjugation, of course. I intersect them all. I get an open normal subgroup. But okay, now let's consider. I claim that over n, things become trivial. N is deep enough down in gamma, so you don't see anything if you go down there. If you take G is GF now. R2, H1, this is the restriction to n. This is 0. Okay, they don't need 0. Is trivial. That means if I'm picking F here, and so F is a map from gamma to G, satisfying the cocycle equation, right? I mean, I'm not saying here, I'm thinking of a cocycle, actually. It's a map satisfying the cocycle equation. If I restrict to the values in gamma 0, the cocycle equation just makes everything a homomorphism, right? So F restricted to gamma 0 is a map from gamma 0 to G, which is a homomorphism. Right? The cocycle equation doesn't have the twisting with the group action anymore, because gamma 0 is the kernel of the action. the image is the group of a certain index, and n is deep inside in here to miss it. By the assumption on the index of n. Okay, let's take it to n. Is trivial. And okay, now here is a classical short exact sequence. I guess I don't know how to. Yeah, now I think I read it in the right order. Probably I missed it the right time. Last time that I did. H1 double n. These are maps from gamma to G, which are 0 and n, I can think of. So in particular, these are maps. Gamma, G, and I can restrict those maps to n. I think this is something I tried to write down at the previous hour, or the hour before, and couldn't do it properly. But there I had a toast here. So this was classical cohomology. Now this is not classical cohomology anymore, but the fact that this is exact is still correct, and this is the standard thing which I will not check for you. And now we know that this map is trivial, so everything is in the kernel, but this means that everything is in the image. But this thing, obviously, I mean, here everything is finite. Hence, properly, but the size of it is less than H1 gamma of ng. Z1 ng, which is just map from this group. Okay, so that's about case one. So here's the reduction. To show that H1 gamma G is finite, it is enough to know that H1 gamma G naught is finite. When G naught in G is the connected component. As usual. Okay, so this reduction, I think you feel that it should follow from that level over there and the long exact sequence, and it does. Just there should be a word of warning. So let me make it. Gamma is. Let me omit the gamma notation here. So I have H1 G naught here. This is finite. And maybe I know that this is finite. And then I should be happy, right? Only I should say something, because I mean, if you take the special point here, the fiber over it will be finite. It will be the image of that one. If you take another point, it is not clear that the fiber over it will be finite as well. It would be clear if I would make that other point my special point. And we have a trick for that, called twisting. So we must twist in order to do this. This is not an entirely trivial thing, but it could be done. Whenever you have where I wrote in my so H1G, now I can inject it into the following thing. F inside image H1G. Sits inside H1. This is a finite set by the previous case one. And now I should look at the image of the twisted exact sequence. So this H1 and G naught F. I should, okay, if F is, let me explain this, but okay, so, sorry. I'm assuming more than that. So I didn't write the reduction correctly. To show that this is enough to know that, well, maybe L for every L connected. I didn't try correctly. I can take an element in H1G. One of a finite collection mapping onto the image here. And the image indeed is finite. With each one, I can twist the G action on itself. I can twist the G structure of a group. I mean, as a group, G will stay the same, but it will have a different it will have a different Galois action on it. G0, geometrically, it will be the same variety, it will be the same space, but it will have, again, a twisted action. But the Galois cohomology of it, still, by this assumption, I need less than that. I just need to apply this to the variety of G0s that I will get here, the twisted ones. And it will be finite, so, okay. Okay.
No, I don't. So for every L, for which L? And also, what is below this? What is the subscript?
Here or here?
No, here, under the.
Okay, so. Okay, let me. This is a 7 set. It is mapped onto, well, its image here, which is finite. And to each point here, there will be the fiber here, over it. And this should represent, the index set should represent the points here. And that thing should represent the fibers over. Okay? Now let's focus on the special point. Exactness of this sequence says that the image of the special point, sorry, the fiber over the special point here is the image of this guy. but this is what I wrote here, ignoring f. But now there is this trick, which I will not repeat now. It requires, I mean, I'm relying on this understanding. I guess I didn't explore this trick much, so probably you should remind yourself this. This is the main issue here. There was this trick of taking cocycle and twisting the structure of G itself. G is a G set. And I can use any cocycle, another element here is another G set with another gamma action. I can use G as a G set, I can use G as a G group actually. G act on G by conjugation. I can twist this by whatever cocycle I see. That's something I was elaborating on. And the whole of this is making, I'll get the same set here, but with a different special point. And that special point will be the point associated with that cocycle. And then exactness will tell me that the kernel will be the image of the image of this, but this twisted guy here will be the kernel of that special point. So altogether, so this is the standard technique. So I guess, yeah, I hope I am convincing. And if not, you should check out these details yourself. But I want to give the idea in full, maybe not all the details. Okay. Oh, maybe just write down some clear after reading. Where G0f is G0 twisted by f bar in A1A. I use the term f bar because it's a lift. Next proposition, or next reduction, enough to consider G reductive. Yes.
I got a little confused by the last part over there.
By
The last part over there. Isn't F already a rank from gamma to G?
well, we may consider f as a map from gamma to G. We had several ways of how to think of cocycles. Either specifically as a map, well, up to equivalence relation of those, which we call the cohomology, or we may think of a cocycle or an element in here as a principal G-homogeneous space, right? With some gamma action, which is not a standard one.
So why should you lift F?
Well, I'm running over f's in the image. I'm running over f's here. I mean, okay, I'm running over. If you want, I'm running over the f bars, which are finite set of representatives. Okay, and when I twist G0, I'm doing it with respect to a cocycle here. Of course, I was using the fact, by the way, that whenever I'm twisting the action on G, I'm also twisting the action on G0 because G0 is a characteristic saddle of G. introduction, and this is particular to characteristic zero. Actually, if I said earlier that some things might work over other characteristics, then not this stage, not this step. We know that G has a level decomposition. So, well, here's something that always there. Let's denote the unipotent radical. This is a normal characteristic again, subgroup of G. And G mod U, or let's call it H, so this is definition, is reductive. This is true in general, what I'm writing so far. But in characteristic zero, I always have a lift, a section here. So G could be written as U times H. So this is something that you, again, it's part of the standard theory, you prove using the algebras. It is fully algebra, this is standard, and so it works for characteristic zero just as well. We now explain how do I use this. So look at, okay, so I have this map and that map. And write those down. So I'm having these two guys, and so if I picking the letter H, I guess it's not very convenient, but as well. I start, I know.
No, so pi should be the left column.
It's contravariant.
No.
No? You have it here.
No. You have a map from gamma to H, then you can view it as a map from gamma to G, and a map from gamma to G
These are the
H.
coefficients, not
Yes, so you have two parameters. You have the gamma thing, you have the
Yeah.
coinvariance or whatever.
It's covariant, and not contravariant.
I don't know the name. Anyway, this is identity, and this is identity. And pi is onto. So what is it that I want to show? I want to show that this pi actually is an isomorphism. I didn't tell you. So by looking at this sequence, I see that it is onto. Now I'm looking at UGH. And I will look at H1G goes to H1H. This is the same pi. But here I will have H1U. And it's zero. Prove that. So pi is injective. Yeah. Again, warning. I can just say that this is because this is zero, then this is injective. To get injectivity, I should do the various twistings. Consider all possible twistings. Consider all possible twisting. So whatever twisting I will make, this still is zero. This still it will be a unipotent subgroups and always zero. And then that the fibers over every map here will be trivial as this map is injective. And all in all, I will get that this map pi is an iso, in fact, and so is its friend S. How are we? I don't want to be late. I guess I should finish now. Okay, we are quite close to the end, but there are still things to say, and we don't meet next week because there is Shavuot, so we meet the week after, and now we can continue from here. So please just read it before or watch the video or something. I will also remind.